Good afternoon. Okay, so we are here for a marathon talk on an extremely boring technique of astronomy. I have a little over an hour to convince you that this is not the case and you were all wrong. Where do I start from? Well, let's see. Some recommended readings. Two in particular that I like to provide to you as references. The Astronomical Applications of Astrometry and the Astrometry for Astrophysics books. That gives you an idea. You have astrometry in combination with astronomy and astrophysics. So probably astrometry has some usefulness to both astronomy and astrophysics. And as a matter of fact, it is so fundamentally important that if you take the astrometrist out of the astronomy pyramid, everybody else falls. And you cannot do any of your interesting spectroscopy work if you don't even know how to point your telescope to a given target. So it is fundamental. And it is fundamental for several aspects of applications. It is fundamental also potentially for the search, detection, and characterization of planetary systems. It has a potentially very simple way of applying the technique. You are seeing a star in the plane of the sky, and you measure its position accurately, and if the star is orbited by a planet, it will be pulled by the gravitational interaction with the orbiting companion, and it will describe some sort of wobble in the tangent plane to the sky that you should be able to detect. And in fact, the magnitude of this effect, which is called the astrometric signature, is a function of the ratio between the companion and the primary, is directly proportional to the separation between the two objects, and is inversely proportional to the distance to the system from the sun. This effect is of order of millisecond type for a star at 10 parsecs from the sun, solar type, orbited by an object like Jupiter on a 5 astronomical unit orbit. So in absolute terms, it's not that small an effect. So the hope is that we'll be able to find objects such as these even with this technique, and we should have found something. The question then comes, why is it that we have not found anything thus far? In the famous mass separation or orbital period diagram that you can plot anytime today, you take it from the NASA Exoplanet Archive, you will find here a list of objects detected with a bunch of techniques, more than half a dozen, and astrometry does not appear, not even with just one object discovered. Is it true? Is this really the case? Are we forgetting something? Is there any conspiracy theory that is conjuring against astrometrists to be able to participate to the exoplanet field of science? Let me try to convince you at the beginning that this might be the case. You were not born, I think none of us was born, at the time in which an Indian physicist was discussing the final evidence through astrometric techniques of the discovery of two planetary systems around stars around the sun, 1943, published in Physical Review. He was going about, oops, no, I should have done that yet, sorry. Discussing also, based on theoretical hypothesis, how many planets you would be able to potentially find in the solar neighborhood of dimensional galaxies, and the outcome of his inference was a couple. So they had found two, they found them all. Sir James Jeans, more famous than this more or less not very well-known Indian physicist at the same time, published in Nature his account of the discovery, discounting the point of view of Mr. Sen, and saying that in fact, no, according to his own calculation in another letter in Nature, in fact, there should be at least of order of 15, 20, maybe 30% of stars having planetary systems in the galaxy, so you should expect a bunch of them. Sounds similar to the predictions that are being found today in the literature. So we're still talking middle of the Second World War. And an even more famous Nobel Prize winner was going along the same line, even coming up with a formula that tells you, as a function of mass, what's the orbital period of the companion you should expect. So find objects with disturbances at these periods, and they will all have the mass of Jupiter or so around stars in the neighborhood of the Sun. Have you heard ever of any of these discoveries being included in the mass period diagram that we have seen before? No. 10 years later, Otto Struve, in another seminal work, was discussing the burning question of the existence of planetary systems in the galaxy, corroborated not only by the discovery of the two objects around 61 Cygni and 70 Ophiuchi that we had seen before, but even, and confirmed, by the way, by observations with independent instrumentation, while additional discoveries by Peter van der Kamp and others. Have you heard of any of these being given to the lot of the contribution to planet discoveries for astrometry? No, you have not. Because, as Eric Ford has shown in a talk a couple of days ago, simulations show that usually claims are more often wrong than right. And in fact, to make a very short story, a very long story short, the path of planet discovery with astrometry is full of blunders, unfortunately. It's a tragic tale that dates back to the 40s, as I said, and continues in the 60s, in the 80s, all the way to just a few years ago, just less than 2010, just before 2010. And all these tentative detections of sinusoidal variations or even fully Keplerian orbits identified in the plane of the sky with astrometric instrumentation from the ground have been proven to be untrue. Not only, even more sophisticated work based on spaceborne observatories, like in particular the Hipparcos spacecraft, if carried out with non-sufficiently robust statistical methodologies, would have inferred, in fact, a population of objects with masses that were not corresponding to the reality because of the quality of the data not corresponding to the robustness of the statistical methods utilized. It is not all bad news. Astrometry has been applied successfully to do something in the exoplanet arena to date. It has contributed, for example, to get rid of some potential planetary candidates, making them rise, again, using, in particular, Hipparcos astrometry constrained by radial velocity orbital solution obtained from the ground, constraining the masses of these objects to be primarily in the brown dwarf mass regime, so much larger than inferred by radial velocity methods. There is, in the literature, a significant number of statistically somewhat significant upper limits that make these objects likely to be planets, because rather than inferring a very large mass to the companion based on, for example, Hipparcos astrometry, there is no signal in the Hipparcos astrometry of the presence of the companion, and this, to some degree of statistical confidence, implies that the planet is likely really a planet. And the minimum mass inferred from radial velocity work is likely to be very close to the actual mass of the companion. There is also work from space that uses independent methodologies. Hipparcos astrometry is an example of, is a first example of global astrometric measurements obtained from space. The work carried out with the fine guidance sensor on the Hubble is instead a very important application of relative astrometry in narrow fields of order of tens of arc seconds or so. And there is a host of, I'm going to learn this. There is a host of relevant work carried out in particular by the group at Texas University that has allowed, for example, actual mass determinations, again, with the fundamental help of constraints on the orbital solutions coming from ground-based radial velocities, for a handful of objects. Some of these turned out to be actual planets in mass. Some of these turned out to be either brown dwarfs or low-mass stars. There's even an important measurement, the first ever carried out directly with astrometry, for the relative alignment of two components in the Upsilon Andromeda system, the C and D planet. These are massive enough to be able to have their own masses and the relative inclination angle measured directly by HST astrometry, providing evidence for a significant mutual inclination between the two. There are a couple of actual discoveries. This is all work that assumes the knowledge of the companion already being there and attempts at astrometry to extract as much information as possible, in particular, improvements in the orbital solution and the actual mass determination of the companion. There are a couple of discoveries. One, which is the one that, in fact, should appear potentially in the exoplanet archive, carried out by the group of Matthew Mothersbaugh, now dating back several years. It's an article of 2010. In this case, sub-second binaries were monitored for the presence of orbital motion in either of the two. So we don't know which of the two is actually being orbited by a planet, but there is a claim for a companion orbiting approximately 2 astronomical units of either of the two of a closed binary system, two of the components of a closed binary system with a mass of 1.5 Jupiter masses. The identification of this object in the abstract of the paper doesn't exist. So you have to read close down the lines inside the paper to find, in fact, the claim of the discovery of this object with a disclaimer, with utmost care in identified by the authors themselves in taking this result as real because of the history of failures in the past decades. This is one object that Gaia, which is to come later on in the discussion, might be able to discriminate whether it is true or not. The latest results in high precision astrometry from the ground come from the use of 8-meter class telescope instrumentation like FORS2 on the VLT, and by taking advantage of relative astrometric measurements in narrow fields, in narrow dense fields with large numbers of reference stars around a target that's typically rather faint. Group led by Johannes Salman has recently published detection of a couple of very low mass companions around very low mass stars at the bottom of the main sequence, late M dwarfs. And in particular, this is the discovery announcement of a low mass M dwarf, low mass brown dwarf to a late type M dwarf. So there is, this is not a planet, it's low mass brown dwarf, but it is still interesting enough because it's a very important demonstration of this technique. I'd like to conclude that this is essentially the overall view of what has been obtained by astrometry so far, with a couple of latest discovery announcements. This is a potential discovery announcement. The nearest planet to the Sun discovered potentially to date. This is milliarc second astrometry of minor bodies of the solar system, identified to be aligned in such a way that they can only be sitting with this orbital configuration if perturbed by a very distant companion with a mass of maybe 10 Earth masses, a super Earth that could be lurking at a couple of hundred astronomical units out in the farthest reaches of our solar system. Jury is still out for this. Another result that I really liked, that we've already seen both as a poster outside and even in a previous talk, is the GPI-based measurement of the orbital motion of Beta Pictoris b, with the fundamental inference that the position angle in the sky of the companion varying as a function of time, this implies that based on ephemerides prediction, the potential transit that many people have been looking forward to characterize in just about a year from now, in fact, will not occur. And this is another fundamental contribution from millisecond level astrometric measurements to the field. Nevertheless, millisecond astrometry, as I have shown, is now recognized of importance to further the characterization of planetary systems that are already known. But when it comes to actual discovery, this is really still tough. You need to do better by 1 or 2 orders of magnitude. Millisecond astrometry is just not enough to discover planetary systems. And in general terms, you have to leap by a couple of orders of magnitude in astrometric precision, similarly to what was done in radio velocity work when it came down from kilometer per second level binary system detection to meter per second level low mass planetary system detection. This can be done in a couple of ways. I mentioned the 2 techniques. Narrow-angle astrometric measurements can be carried out using a set of reference stars, both from the ground and in space. There is, I may not actually ever learn this. The gravity instrument on the second generation instrument on the VLTI is promising very high precision narrow-angle astrometry. The Theia concept, that is a proposed mid-sized mission, may do of order of a factor of 20 to 50 better than Gaia, down to the sub-microarc-second level. If you're attempting global astrometric measurements, this can only be done from space, and as of today, only Gaia is in the game, and we will come to that at some point further down the line. Before we talk about Gaia and its potential for exoplanet discovery, I have to spend of order of, some slides. I'll try to breeze through them so that you don't get too bored. With a recap of what you need. What are the ingredients that you need in order to carry out planet detection robustly with astrometric measurements? Well, the first thing you need is a correct model of your observable. The observable is typically, depending on what you're looking at, whether it's a space-borne observatory like Hipparcos or Gaia, or it's a two-dimensional reference frame, locally defined in your instrument, both on the ground or in space, is typically one estimate of the angular position in the sky of the target of choice. This is usually defined in a reference frame that needs some degree of transformation because it's locally in a reference frame that is particularly defined given the instrument you're using, and then you have to map it out in the, on an actual celestial direction. The estimate of the position of your target will contain information on several things. Certainly on the way the target moves on its own, proper motion and parallactic motion are the primary component of stellar motion for a star that is not orbited by any companion, and it may contain then any element of information that is fundamental to characterize the orbits and the masses of the orbiting companion that may be there. To this, you have to add a set of more or less well-known or well-characterized physical effects that must be correctly modeled and pertain to the general environment that is sitting between you observer and the star that is being observed, and pertain to the position of the observer, the observed, and the relative motion between them. Very quickly, depending on your instrument of choice, you always have to deal with the general transformation. As I said, you observe in some reference frame, you want to define the position of your star in the celestial frame, you have to do a transformation that can be a generic rotation matrix, can be a plate constant modeling procedure, can be anything, can be for interferometers in the next slide, can be a projection of the stellar position on the baseline of the interferometer. There is always some level of this type of transformations involved, and there is a large amount of potential uncertainties involved in doing this measurement process. Remember, before you reach planetary parameter determination, you first, unlike the case of radial velocity work, for example, you first have to model the stellar motion without any planets. So you first have to model the linear component of motion due to the stellar proper motion in the, say, for example, in the tangent plane, plus the yearly parallactic motion induced by the observer rotating either sitting on the Earth or at L2 or in an orbit around our planet. Once you've done that, next slide, you can determine the planet parameters. The planet parameters come in the number of 7, some say 6, I like 7. The general modeling is done as linearly as possible. Planetary parameters typically are 7 and are nonlinear. There is a way of making the modeling of planetary parameters in the tangent plane of the sky, for example, through this approach, as linear as possible, with 4 linear parameters essentially coming out of combinations of the semi-major axis of the orbit of the companion and the 3 general angles that define the orbit orientation in the sky, plus a non-reducible to linear component that remains nonlinear, that contains the other 3 parameters of the planetary motion that have to be dealt unavoidably in a nonlinear fashion. This is the basic of your model. Whatever you try to model will come with some noise terms, and I will spend the next 2 hours just telling you what is the set of sources of noise you can find in astrometry. Okay, I'll try to diminish this. The noise sources come in, as you have heard, ad nauseum from the beginning of the workshop in a couple of fashions. Systematics, random noise components, correlated noise dominates many of the observations with other techniques. It does dominate as well in astrometry. Very quickly, there is a fundamental limitation, which is your diffraction limit, which is guided by the resolution of your instrument. I want to focus your attention only on the order of magnitude of the impact of these terms on the measurement uncertainties that we are going to keep in mind. For reference values such as these, diffraction limit tells you that you should not be able to do much better than a few tens of microarc seconds. This is a fundamental limit that is difficult to overcome. If you're sitting on the ground, you have 2 additional complications. You have one that I really hate, which is DCR, diffraction chromatic refraction. This is extremely complex to model, no details. You can read the slide and eventually ask questions later if you're not sleeping. The global effect of DCR on the uncertainty of your positional measurements is typically estimated of the order of milliarc second for ground-based work. Then you have the atmosphere that not only works against you to provide differential chromatic refraction effects, but also has turbulence. And turbulence is, again, very difficult to overcome. There are subtle ways of getting around typical limitation of the order of milliarc second level that bring it down to maybe a factor of 10 using, for example, adapted optics and the choices of very dense reference frames, such as the work carried out with the VLT and the FORCE-2 instrument. So 100 to 1,000 milliarc second level budget term. There are elements of systematic noise that pertain to the realm of instrumental problems that you can identify, depending on the configuration, whether you have a monolithic telescope or a diluted configuration, an interferometer. These numbers, for example, for Gaia in space, basically are dominated by the possibility of centroiding very accurately within a very small fraction of the pixel, the position of the point spread function describing your stellar target. And in this case, we are talking about of order of a few tens of microarc seconds. A little bit larger is the estimated component of additional systematic noise that is expected, for example, for gravity at the VLTI, that takes into account primarily the uncertainty in the determination of the length and variations in the baseline of the interferometer itself. We're not done yet. If you're in space, you get rid of the atmosphere, there's no DCR effect, and everything is fine. However, your spacecraft moves around. And there is a host, an unbelievable list of potential error terms you have to take into account related to the class, the family of attitude errors in your spacecraft that you have to deal with. And any spacecraft is different. There is no two models that can be used for the same. When it comes to attitude modeling, and you have to take every specific case with a specific different approach. There are general families like the impact of micrometeorites, radiation, drifts, jitter in the spacecraft. There are general families, HST as all these, for example, that have to be modeled when it comes to precision astrometry with a fine guidance sensor. But the case of Gaia, for example, is completely different because of the way the spacecraft moves in space. Very specific to depending where you place your spacecraft is also the problem of particle radiation from the sun. This is the latest addition that used to be an extreme source of worry for the Gaia consortium. The peak of the solar cycle coincided exactly when Gaia essentially was launched at the end of 2013, and the potential impact of heavy ion bombardment on detectors was deemed to be potentially a big source of additional uncertainties in the astrometry. To date, it doesn't look as bad. There is a lot of other sources of noise that we will see when we come to discussing the Gaia workings later, that has actually become much bigger of a nuisance than particle radiation from the sun. Are we done? Oh, yes, for some degree of some level of noise sources. Then there is another level of noise sources you have to take into account. These are astrophysical in nature. They come in a couple of flavors. As long as you are capable of modeling them, the ones that are go under the term of relativistic corrections can be understood. The ones that comes to the general gist of astrophysical jitter are much less difficult to understand and certainly to model properly. There is a class that is of interest only for the nearest stars to the sun, and probably for Gaia hardly so anyways, which is secular changes in the proportional parallax, driven particularly by the value of radial velocity of the star in object. The magnitude of this effect is typically of order of microarc seconds, if not smaller, already for stars within 10 parsecs or even less in the case of the variation on the secular change in parallax. So this is a number that can actually be predicted and corrected very accurately for. So you just have to correct for it. It's not a big deal. The two important relativistic corrections we have to deal with are light deflection And at the level of precision of Gaia measurements, you do have to take into account not just the perturbations to the light path due to the sun, but in the local solar system, you also have to take into account at least the larger planets and some of the biggest minor planets. They do contribute at the level of tens of microarcseconds, even far away from the sources of gravitational deflection. And finally, there is relativistic correction to the classical concept of aberration. This is done today in the general relativistic modeling of the Gaia observable, for example, down to the microarcsecond level. So the level is probably better than 10 times the required, the best case measurement accuracy of Gaia. So this is also a correction that is most likely done very accurately. No big deal there, hopefully. Then comes the astrophysical jitter intrinsic to the source and its environment that you're looking at. And this can be a big trouble. Stellar binaries, for example, can superpose a very large effect that can be linear or non-linear, depending on the time of the phase that the orbit is sampled, superposed to a much smaller effect, a much tinier effect of orders of magnitude smaller, that could be the one induced by a planetary companion orbiting one of the two, the primary in this case, for example. And the coupling of the linear component of proper motion of the primary plus potential orbital motion from a binary, depending on its phase, can complicate extremely the interpretation of any additional signal that you would see coming potentially from a planetary companion orbiting the primary. There is also, in a matter of principle, the problem of positional jitter due to variable surface structures on the primary of choice of yours that you're looking for planets around it. The situation is not as bad as in the case of radial velocity work. For radial velocity work, we have heard from Javier, from Deborah, at the beginning of the workshop, that this is the fundamental limitation today. The star, as of today, for Gaia type measurement, the star is not the limit. There are other issues, as I've shown before. Typically, for main sequence stars in the neighborhood of the sun, we are well beyond 1 microarcsecond, or in the ballpark of 1 microarcsecond level of disturbances. So if you are 20 times more accurate than Gaia, then this is becoming a problem. If you're not, this is not a big deal. If you're looking at binary companions around very large guys, this is a potential issue, but we'll not get into that. Yeah, there is also stellar rotation, but the stellar rotation astrometry couldn't care less, doesn't see anything, it just looks at the position of the star. And finally, you have a variety of potential noise sources induced if the star is somewhere embedded in a protoplanetary disk. There could be geysers or debris or whatever. These go by estimates of their impact on the order of typically tens of microarcseconds. Some of them have timescales that are not very interesting, at least for in terms of possible coupling with orbital motion. This is the case of potentially gravitational unstable disks, where the disk self-gravity has typical action at tens of astronomical units from the primary, and so the timescales of these motions are hundreds of years. So not a particularly big deal, given the amplitude. Others can be a little bit more of a nuisance, such as the variable illumination of the disk due to an orbiting planet that is sweeping material while it's going around, because the source of the noise goes with a period that is similar to the orbital period of the planet. The latest just appeared in the literature is the identification of potential effects at the much smaller size, level of microarcsecond, induced by structure, individual elements of structure in the disk that can also induce displacements in the stellar photocenter. So have you done the sum of the magnitudes of the orders of the impact of all these noise sources? So we are also almost ready then. We can move to getting out the planetary parameters given a proper model of your observable and a very good understanding of your noise. And the way you estimate your planetary parameters is in a fashion similar to all the other techniques that we have heard about until today. And similarly to all the other techniques that we have heard about until today, you have similar problems. And you have to define your best statistical methods, your most robust possible procedure for parameter estimation, whether it's in a frequentist approach regime or in a Bayesian. Here we are strongly biased against the frequentist approach. So bias inference will certainly be of most likely the choice. And you also have to properly model your parameters uncertainties. And this again comes in a variety of flavors that will be related and directly connected to the type of choice of the estimation process that you make. This makes up for essentially the introductory part on the bad things of astrometry. The next point is talking about Gaia. How much time do I have?
You still have 29, 30 minutes.
We're good. Okay. So I'll spend 29, 30 minutes talking about all the problems Gaia has, and I will tell you nothing about the science. How does that sound? Okay, so just breeze through the problems of Gaia and tell you something about the cool science that can come. So we are up there since now almost 2 years. Gaia has this scanning law way of measuring the whole of the sky within 6 months. And it does it like Parkhurst did with two fields of view separated by 106.5 degrees, the basic angle. It revolves all around the sky and covers the full sky in 6 months in a pattern that is highly position dependent. The scanning law is such that depending on the location of your target, the target may be lucky or unlucky. It may receive only a few tens of observations in some regions of the sky. It may receive maybe 200, even more than 200 data points within a 5 years time span of the nominal mission of the duration, depending on location in the sky. It comes with the largest focal plane ever built for space-based astronomy. Now, if you look at the LSST equivalent from the ground, it's 3 times bigger than this. But in space, this is still the biggest thing yet. And it performs 3 types of measurements. The largest chunk of the focal plane has of order of 100 CCDs devoted to astrometric measurements. There is photometry, in particular spectrophotometry, in two bands, one blue and one red, and then there is the possibility also of gathering spectra with a radio velocity spectrograph. Gaia primarily observes along its sensitive direction, the scanning direction. It also performs 2-dimensional measurements, but the one that is really sensitive is the one along the scan. The across-scan measurement is typically of order of several times worse in terms of positional precision. We're in routine operations since, as I said, August 2014. The numbers of data collection are massive. These are the ones as of May 2015, so now you have to more than double these numbers, both in astrometry, photometry, and spectroscopy. It's really a massive data collection. Okay, it will be dwarfed by LSST, but you know, from space, this is still massive. It has the capability of observing even very bright stars down to magnitude 2 G-band. The ones up to magnitude 3 will be processed as any other star, even down to the faint end of 20.7. Objects brighter than them very few, in fact, hundreds of stars or so, will have to be modeled separately because they are too bright. They leak too much, and there is no way of getting them in the general data processing scheme of Gaia. So I told you about the fact that one of the biggest worries of Gaia was charge transfer inefficiency by CCD damage from heavy ion bombardment from the sun. When commissioning started, the most important focus of the understanding of what was going on with the satellite was not this source of noise, but several others that popped up and have a complicated interpretation of the data thus far. This is the shopping list that you see here. The one right at the top may be a potential source of concern also for JWST. I don't know if CHES, maybe I shouldn't say anything about that. So it is a concern for Gaia. It has complicated the life, particularly at the faint end, with the worsening of the unavoidable worsening of the astrometric performance, photometric performance, and spectroscopic performance at the faint end of the instrument gathering data gathering. Other ones are more or less well understood. Some have provisions, such as the transmission losses, for significant mitigation or completely getting rid of them, to mitigate transmission losses, to do ice forming somewhere on the mirrors. We heat up the spacecraft to 20 degrees room temperature, then it goes down for a couple of weeks. It's not good for the spacecraft, but it's a way of getting rid of it. And unfortunately, there have been already something like almost a handful, 4 at least, heating up and cooling down procedures that have had to be undertaken to cope with this problem. This is the most interesting one. It was not supposed to happen. The basic angle monitoring device was supposed to tell us that the baseline, the basic angle of 106.5 degrees between the two fields of view was constant within a very small number that in angular units corresponds to microarc seconds. And the basic angle monitoring device is actually measuring variations of this basic angle of the order of 3 orders of magnitude larger, milliarc seconds. This is something that was not supposed to happen, and I probably should not say more why this is happening. What I'm saying instead is that there are mitigation procedures also being put in place. This is essentially quasi-periodic effect that can be modeled to a good extent and subtracted, but not modeled perfectly yet. And so one of the impacts of this incomplete modeling is eventually convolved in the data products that will come with the first data release of Gaia. The most important number that I want you to bring home is related to the single measurement precision estimated to be achieved by Gaia, because this is the number that eventually gets folded in when it comes to planet detection. And is of order of a few tens, maybe 40, 50 microarc seconds, typically with some variations due to the gate scheme that tries to cope with very bright stars that are brighter than 12 magnitude or so, per CCD. We have a row of 9, so at the end of the observation, coupling the position measurement precision out of the row of 9 CCDs is of order of between 10 and 20 microarc seconds, slightly depending on spectral type. This is the very best that Gaia is expected to be able to do. As I told you, there has been an impact on the overall science performance at the faint end due to the complications at the time of commissioning. The bright end is essentially unchanged. These numbers still hold up to 15 magnitudes or so with respect to the specifications prior to commissioning. The faint end suffers by almost a factor of 2 in both astrometry and photometry. Now, before we come to see what Gaia can do in the realm of planetary science, first we have to subtract the stellar motion. Gaia is deemed to observe a couple of billion stars in the sky. So it's also deemed to observe a very large number of objects for a very large number of times. How do you deal with that? Well, there is a scheme called Global Astrometric Solution, which is essentially very similar in philosophy to what had been adopted by, for the first time in the reduction of the Parker's data. And the general gist of this approach is that you end up with a general astrometric solution that has a very large number of unknowns and, fortunately, much larger number of measurements to deal with. Still, it's a massive number. You know, with 3 unknowns, you can feed an elephant, says some. So hopefully nothing very strange will come out of this, but only very good science. It will be done in a purely least squares solution kind of approach. So this is frequentist. There's going to be essentially no Bayesian way of doing things in the actual Gaia alone processing of the data set to derive the 5 basic astrometric parameters. Prior to that, before you find anything that is departing from single star behavior. Now, last but not the least, the data almost coming up. The first release is in just a few months from now. On the 1000th day of the mission, there will be the release of a couple of million parallaxes and proper motions of Tycho stars. There will be positions in the sky for all stars detected down to the magnitude limit of the survey. This will be followed in approximately an additional year time by the release of 5-parameter astrometric solutions for well-behaved stars across the whole of the sky down to the magnitude limit of the Gaia survey. I mentioned briefly what is the astrometric content of the Gaia survey. A little bit more elaboration to provide a couple of caveats. In particular, there will be additional information on the realm of applicability of the results for the Tycho Gaia astrometric solution with, I hope, the most detailed documentation explaining why this should be taken not just as face value, and when you will be using parallaxes for any application or proper motion for any application, take into account that the modeling of the astrometric data of Gaia is still incomplete. Now, planets. Planets orbiting stars that do not look single in the Gaia data. And there is a particular coordination unit within the Gaia consortium that deals with the data processing and analysis of the Gaia data that is called, in fact, non-single star treatment. It treats stars that do not look single in all of the 3 channels of Gaia, photometrically, spectroscopically, and astrometrically. And then eventually, information from variability in radial velocity, variability in photometry, and variability in astrometry gets potentially combined in a solution combiner that may deal with, for example, a combination of objects that show up as eclipsing binaries and also spectroscopic binaries, spectroscopic binaries and astrometric binaries, and all permutations. The astrometric binary solution sits at the bottom of a chain for what concerns the astrometric treatment of the Gaia data on non-single stars that eventually deals, right at the end, with planetary systems. This is the chunk of the processing chain that, when everything else has failed, I will not go in the detail of what are the various models that gets tried before I can accept questions on that. Eventually, you start modeling extrasolar planetary orbits. Just a reminder, we talked about the general model of observing the motion of a star with its orbiting companion, for example, in the plane of the sky. Gaia observes at any time with a scanning direction that will not be aligned with the plane of the sky most of the time. And so you have to, again, perform another transformation. And the value of the scanning angle must be known very precisely because it contains all the information on all the calibrations and all the modeling and all the corrections that have been made prior to the search for planetary motion. If this one gets estimated wrongly, you may begin to see things moving around. That may not be the case. Learning from the lessons, for example, from radio velocity surveys and other techniques, we have a multiple technique approach in the determination of planetary orbits within the Gaia pipeline. There is a genetic algorithm approach, and there is a differential evolution Markov chain software chunk that are carrying out independent solution. Eventually, they get checked for consistency, and in the case of multiple systems detected in Gaia astrometry, there is also an element of check on the dynamical stability of the solution that you have obtained in either of the two channels or in both. I have 10 more minutes, I hope. Perfect. So let's conclude with some positive news. Gaia is going to give you many, many interesting results in exoplanet science. I will spend one slide on the possibility of the impact of Gaia photometry, particularly in the field of transiting planets. This is not very well characterized because of the difficulty in getting good sampling of the transit event with a very coarse coverage of the sky of Gaia data. Typically, you'll end up getting usually very few points in a transit event. The photometric precision at the level of millimagnitudes is certainly enough to detect, for example, giant planetary companions, but the detection efficiency will be an extremely strong function of orbital period. Very close-in objects will be seen possibly in the thousands. But in order to get these detections, you will need a very large reservoir of stars. Only a few of these will be sampled long enough to have the planet detected. And this means that typically the objects will be faintish, if not very faint. So this is the biggest caveat in the potential yield of transiting candidates coming from Gaia data. There may be many, not as many as Kepler. They will be giant, they will be close in, and they typically will be orbiting faintish stars. Astrometry has the potential of the largest impact in the field. Again, forget about the rest. Focus on these two curves. This is the detection limit for a solar-type star at the distance of Taurus Auriga, star-forming region. This is the limit for planet detection around, let's say, low-mass M-dwarf in the neighborhood, within 20-25 parsecs or so. If you see the scale, we're talking about, regardless, giant planetary companions, typically a significant fraction of an astronomical units, all the way up to maybe 4 or 5 or so. So it's, again, giant planets. The realm of super-Earths and certainly habitable companions that are rocky in nature is entirely out of question, is completely out of reach of Gaia. To give you an idea, even the nearest stars to the Sun provide in the habitable zone objects that would give super tiny angular sizes of the perturbation. For Gaia astrometry, this is well beyond the detection limit. But the sensitivity of Gaia to giant planetary companions may be counting in millions of stars. And so if you have millions of stars around which you can detect planetary systems, be them only giants, then you have a potential reservoir that, depending on who you ask to, estimates of order of tens of thousands the eventual reservoir of planetary systems that may be found by Gaia. And this is the largest single most important impact of Gaia in the realm of exoplanets. To give you just one example, you will be able to do the job that today is done to characterize, for example, the dependency of planetary fraction, of giant planetary fraction as a function of stellar properties like mass and metallicity. Today, this is done, if you look at radio velocity work, looking at masses, not radii, with typically of order of tens of stars in a bin. And with Gaia, you'll be able to do this with tens of thousands of stars in a bin. This will be a gigantic impact. For those who like giant planets, if you only like habitable super-Earths, then the information from Gaia will be somewhat indirect. There will still be. I will give you a few more concluding slides on the potential of Gaia to address issues in many other fields. This encompasses, for example, the realm of post-main sequence stars. Gaia being so democratic, it doesn't matter whether the object has a very different strange spectrum, whether it's evolved or not. For post-main sequence stars such as white dwarfs, it may provide a spectacular observational test of the existence or non-existence of intermediate separation companions that, after the post-common envelope evolution of the giant before the white dwarf stage, should not be there and should have been kicked out entirely. Or we may even find massive objects around brown dwarfs. As of today, there is only, that I know of, tentative detection of planetary companions by microlensing events around brown dwarfs. The late M to L transition region for a primary will be accessible by Gaia, maybe on the order of 1,000 objects, with sufficient sensitivity to planetary massive planets. If they're there, Gaia may pick them up. But to conclude, the impact for the next decade that I like to try to sell as revolutionary for Gaia is the one that is seen and not just looking at Gaia data themselves, but when Gaia is combined and seen in synergy with any other conceivable planet detection and characterization program that you can think of. Just one example for all, the synergy with radio velocity programs. There are several aspects you can think of in terms of combining Gaia data with radio velocities. The general aspect will be the possibility of characterizing completely planetary systems in which, for example, radio velocity sees objects that are only closer in that Gaia has missed because of lack of sensitivity, and Gaia picks up massive companions that are seen further out, and the combination of the two improves the characterization of the system across a very broad range of orbital separations and planetary masses. But this potential synergy goes very much it has a very long reach. Just think about the possibility of maybe measuring the actual masses of order of 50% of the known radio velocity planets to date. There will be a fundamental impact once you combine these two techniques. There will be fundamental impacts. I'm taking a few more minutes. Once you will begin combining Gaia data with direct imaging devices, observations. The overlap, for example, between Gaia and devices such as SPHERE and GPI may be relatively marginal. It will be understood in terms of drift in Gaia astrometry that may constrain to some extent the mass determination for the object that is seen in direct imaging. There will be certainly a much bigger impact in terms of actual synergy with full planetary orbits determined by Gaia and potential direct images obtained with the ELT class of instrumentation. And even there may be some interesting news that Gaia could deliver to you in terms of transiting systems further out. if the object is well sampled and the star is relatively bright and is not very far away, and a quasi-John solution with an inclination angle in the orbital solution close to 90 degrees may be found by Gaia with an uncertainty of maybe a degree or two. This tells you that the planet is potentially a planetary, a transiting planet candidate. And this could be the case for objects with maybe 1 or 2 years of period, or maybe 3. Most of the ones that will be found, there are estimates that could be in the hundreds, will not be actually transiting because the probability of transit is very small at those distances. So out of 100, maybe 1 will. But even 1 would be valuable because these are very cool giants that, as of today, are a class of entirely not studied objects in terms of, in particular, atmospheric characterization in an intermediate separation regime between the ones that are very close in and are seen routinely with the transit technique and the ones that are seen further out with direct imaging devices. There is target selection, there is Kepler up north, there is potential combination with Gaia astrometry. I think I'll conclude here with a word of caution. Astrometry is difficult. It has failed for many tens of years now, but it's doomed to stop failure. And the promise of Gaia is really there, and it will begin to show up in just 2 years' time. The first orbital solutions should pop up by the middle of 2018, so stay tuned. Thank you. Yeah, so the question is Gaia going to get extended? And the answer is the odds are very high. The amount of extension is very uncertain. There is a potential provision for the instrument to last 10 years. We have sufficient fuel in the microthrusters that allow for the small adjustments in the Lissajous orbit of Gaia Del 2 that will allow operations to be run routinely for 10 years. At year 5, there will be clear check at the end of the nominal mission on the status of the performance of and the quality of the data. At that time, we will see how far in the Gaia mission can be extended. We are getting already organized now to begin asking for extensions. I think just like NASA, the extension rate will be only 1 year at a time and will be routinely checked. But an extension is certainly going to be granted, the more the better, naturally. 1 year, in particular for orbital solutions, will not be a huge impact. 8 to 10 would already be very, very important.
So you also talked about gravity, and I was wondering if you could comment on the complementarity of Gaia and gravity. I mean, I'm thinking about, I have my favorite system. Should I go mine the Gaia archive? Should I write a gravity proposal?
The combination of potentially of ground-based astrometry with gravity and Gaia is certainly there. I had the slide before on the potential synergy with ground-based work. Certainly, it will be important because for a couple of reasons at least. First of all, if you have benchmark systems, you can check with both techniques. Those will also be granted potentially an overlap in the time frame of observations. Gravity is starting now. Gaia is there for 2 years. It will continue for another 3. And so the application of the combination of the technique to well-defined benchmark systems certainly should be extremely helpful, well chosen, such that the element of information from gravity can add either time baseline or elements of information that, for example, can characterize better the environment of the objects. So stars of specific sets of spectral types of age would be probably more favored rather than others.
Will the first data release contain time series measurements?
No, and Yes, the first data release will contain time series of any type, and the answer is no. There will be an initial set of time series, primarily at photometry, coming from the second or more likely the third data release. If you're waiting for astrometric data, those are going to come only at the end. For essentially an operational reason that was the same that applied to Hipparchus. The evolution of the data continues as a function of data gathering because of the different way with more data and with more time span the global sphere solution behaves. And so the final word will only be given once. At least that's the baseline approach within the DPAR consortium. When the data gathering is finished, that's the last word on the general solution of the Gaia astrometry. Then the equivalent of the Hipparchus intermediate astrometric data will be released, but not before then.
Questions?
What would Gaia be able to do for the Kepler stellar catalog? What kind of refinements can we expect?
The question is, what can Gaia do for Kepler? In general, for transient work, and for Kepler as well, the most obvious application will be to redo the analysis. I have the slide right here so that we can make the discussion quantitative. In the Kepler field, work such as this that estimates planetary fraction as a function of orbital period and planetary radius puts in each of these little boxes a number of stars that have uniform sensitivity to a planet of given radius and given orbital period. You estimate that fraction of stars that are sensitive based on estimates in particular of their radius. And the planetary radii, as most of you very well know, are crucially dependent on the estimate of the accurate stellar radius of the primary day transit. The planetary radius is the one parameter that will be re-estimated once accurate Gaia parallaxes will be available for the whole of the Kepler target sample. And so you will get in these boxes and redo the exercise much more, not just much more precisely, but much more accurately, because the direct distance measurement will really provide the exact location of the star away from us. And so you can expect certainly a redefinition of this set of diagrams based on the information from direct distance measurements from Gaia. In the case of the Kepler target sample specifically, this is the work that will be done starting next summer, not this one, but the summer 2017, because the magnitude cutoff at approximately 11.5 or 12 due to the Tycho catalog parallax determination of the first data release will not allow to do this work for the majority of the Kepler stars. But that's the most obvious application of Gaia information in the Kepler field.
Did you say we won't get the stellar radii measured for all the Kepler stars?
You will get exquisite parallaxes from Gaia, and so you will redetermine the stellar radii not only precisely, but accurately. And this reanalysis will eventually be redone unavoidably. So the question is, what's my opinion on the decades of blunders in precision astrometry for planetary work? The answer is a little bit of both your points. It was the easiest technique because positional astrometry was astronomy was the one that had been done since the beginning. And so it was the easiest technique to be used for detection of planetary motion at the beginning of times, all the way back to first half of the 20th century. So it was a natural choice, and already a long time back it was recognized as a potential critical question to answer. And so people, after decades of observations, there were already decades of observation gathered just to obtain the results of the false detections of 61 Cygni and 70 Ophiuchi in the 40s. They had to publish. So there was a push, in my opinion, to make the data public. And there was an interpretation that was seeing these variations that was making a strong case for them to go after the potential detection of a planetary companion. This doesn't mean that they were not carefully looking at the data. The data may have actually said that those variations were there, but the interpretation of the nature of the variations for specifically objects such as the ones that turned out to be fake in the 40s and the 60s was the point in which failure occurred because of the incomplete understanding, not necessarily done on purpose, but simply not complete understanding of the systematics of the instruments that they were using. Later on, in particular in the case of the reanalysis of Hipparcos data much more recently, that turned out to be incorrect, there it was instead an application to data that were not good enough of statistical methodology that was not robust enough. And as a result, you were obtaining results that were strongly skewed, strongly biased, and they were simply not, again, interpreted correctly. So there are two families of problems that were faced. One due to the uncharacterized or not fully comprehended behavior of the instruments used. In the other case, the insufficient quality of the methodology as applied to data of not sufficient quality.
Thank you, Alessandro, again.